Hello everyone, this video is for the presentation of CVPR 2024 paper towards high-fidelity artistic image vectorization via texture-encapsulated shape parameterization. All authors are from Shanghai Jiao Tong University. The motivation of this paper is to rethink how to represent an image. We know that the vision concepts come from the nature, and nature is continuous. However, current computer vision researchers tend to utilize fixed and discrete grid-based pixels to represent images, that is, raster images. Nevertheless, pixel-based representation is plagued by numerous limitations. On one hand, it suffers from excessive redundancy due to its storage on fixed grids, which inherently constrains image resolution along with inevitable information loss during image rescaling. On the other hand, pixel-based representation stores all the information of the image in the RGB values of the pixels, resulting in a high coupling between the representation image geometry and texture. Hence, it is challenging to edit the image geometry and texture of a raster image separately. Vector images embody an alternative paradigm for representing visual information, which describe images with a collection of parametric geometric primitives, like curves and closed shapes, defined as control points in the continuous space. Compared to representing images with fixed discrete grids, vector images present many advantages. Firstly, vector images are resolution agnostic. Model images with continuous parameters enables the storage and generation of images in arbitrary resolutions without information loss. Secondly, vector images are easy to edit because they have explicit and explainable parameter format, facilitating convenient image editing ability by simply modifying shape or color parameters in a structured way. Finally, vector images hold the nature of compactness. The shape primitives in vector images are typically defined by mathematical functions, allowing for the expression of complex shapes with a minimal number of control points. Hence, the number of parameters required to store a vector image is significantly lower than that of raster image. Unfortunately, while vector images possess so many advantages in representing geometric information, they fall short in effectively capturing the texture details from the images, which restricts their applications to simple images like icons and emojis. The underlying reason can be attributed to the fact that traditional vectorization representations store a single color within each shape, rather than capturing the distribution of colors. To address such limitation, we are motivated to enhance current image vectorization methods by exploring representing rich textures with compact vectors. We follow the emerging implicit neural representation scheme, which is parameterized into a lightweight MLP that takes the local Latin encodings of coordinate information as input and produces local texture. Drawing inspiration from distributed implicit representations, these local codes are spatially distributed into each control point or geometric representation. And this is the overall framework of our method. Our framework decouples the raster image in geometric space and texture space using a texture-encapsulated shape vectorized representation. That is a parameterized shape representation and a shape-anchored implicit neural texture representation. We utilize the closed Bezier shapes defined as coordinates of control points to represent the fundamental geometric information in the image. Then we use a shape-anchored implicit neural texture representation to explore image textures. We evaluate our texture-encapsulated shape representation on image vectorization task by measuring the differences between the input raster images and the rasterized vectors, compared with sorter methods diffusion and live. We can observe that our representation models the texture details much better than other methods, and effectively prevents local texture artifacts caused by the stacking of redundant shapes. We also make comparisons with general implicit image representations. In this session, we compare methods with Cision on the task of image reconstruction with neural image representations. We demonstrate the efficiency of our texture-encapsulated shape representation by comparing the image reconstruction errors and the corresponding number of parameters required. We can see that our method achieves better image reconstruction results with a significantly higher parameter comparison ratio than other methods. When using the same order of methods or parameters, our reconstruction results are obviously better than other methods. We also show some decoupled editing examples. Our method can easily transform geometric shapes and replace the textures within the corresponding shapes with specific ones, like a frosted glass texture. In the bottom row, we show the shape decompositions with the X marks indicating the control points. And that's the introduction to our paper. Thank you for listening.